Hi, welcome to Casual F Sharp, and today we're going to be talking about discriminated unions. And this is really a kind of companion piece to the episode about pattern matching. Really, you can't use one without the other. But it kind of doesn't matter which order you watch the episodes in. Once you watch them both, it'll all make sense. Discriminated unions are kind of like enums, if you're used to enums in other languages. But they're only like that in the sense that pattern matching is like a case statement. So it's a useful way of starting to understand them, but you have to move away from that concept fairly quickly. Just to make that a bit more concrete, we're going to look at a game called Monopoly. It's a popular board game, certainly here in the West. And if you're not familiar with Monopoly as a board game, just go to Wikipedia and look for Monopoly game and have a very quick look through the rules. So anyway, we're going to use Monopoly as our kind of case study. And if you look at the board and the game, you'll notice, for instance, there are a number of things we can kind of list in order to model the game. So we can talk about a player, and the kind of players or the tokens they can play with are a little sculpture in the shape of a boot. So a player might be a boot, or a player might be a battleship. These tokens have changed a bit over time, but you get the idea. A player might be an iron, in the sense of a thing you iron clothes with. So we've modelled that aspect. I won't do them all, but you get the idea. We've modelled that aspect simply by listing the possible cases. And we're assuming for modelling the game that we don't need to know anything else about the player. So at this kind of logic layer, we don't know the name of the player or whether it's their turn or anything like that. Likewise, there's another little domain we can model, which is the colour. I'm going to spell that the UK way, just to be annoying. And this is the colour of a street. In Monopoly, players can buy streets and put houses on them, and when other players land on them, those other players get charged. So the street colours are brown, another colour is light blue, another colour is what I'm going to call magenta, and again there are a few more than that, but you kind of get the idea. And again, because this is just the game logic layer, we're not worrying about what the particular RGB values are, we're just interested in listing the states that the colour can be in. So let's be a little bit more challenging. Let's try and model the state of development of a street, because buyers can, once they've bought all the streets of a particular colour, they can put houses and hotels on the street, and that enables them to charge more rent when another player lands on the street. So a street might be empty. A street can be empty. Notice I'm being very careful not to use nulls as a flag for something that isn't a thing. I'm going to use a very explicit empty case. I'm just going to jump ahead a little bit and say, well, another state is the street has got a hotel on it, which is the maximum kind of multiplier on the rent, but you can only put one hotel, so there's no sense in saying it's got n hotels. However, with houses, which is the intermediate state, it's got some houses on, and here, this is why I wanted to get to this in our talk about discriminated unions. We can have a number of houses, so I'm going to say that's a kind of label for the case, or the case payload I should say, and its type is an integer. And I missed out an equals sign just here. There we go. So the state of development of a street can be it's undeveloped or empty, it's got a number of houses on, or it's got a hotel, and those states are mutually exclusive, so they're very great candidates for being discriminated union cases. I have not bothered, by the way, here to try and constrain the possible numbers of houses that can be on the street, although that is in the rules, the maximum is 4. It is possible to model that in F Sharp. It's a little bit of a faff. I'm just going to dodge that whole situation, but watch out for a future episode on single case discriminated unions where we might come back to that topic. So there we are, we've modelled the state of development of a street. Now we're kind of in a position where we can maybe start thinking about modelling one of the squares that go around the edge of the board. So let's call those a location, and a board location might be a street, and we can kind of put in some attributes for the street. It's going to have a name, and these attributes are tupled together or tupled together, so we put a star between them. It is going to have a cost, and the costs are integers. In Monopoly there's no kind of cents or pennies, so we can just say the cost is an int. By the way, if I wanted to make that kind kind of defer that decision and make it easy to change, I could actually have a type alias. So I could say type price is actually an int. That's not a discriminated union, that's just a type alias, but it just means I can say price here. Then if I change my mind, it's going to be a float later. In principle, I only need to edit that line. And then we're going to have a color, which is simply our color DU. And we're going to have a state of development, which is our development DU. And one of the key elements of the game of Monopoly, oh, by the way, we need stars here. One of the key elements of the game of Monopoly is the kind of a rental list you get, which determines the various rents for the various states of development when another player lands on. So you can say rentals, and I'm going to make that an array of prices. And finally, a street might have an owner, so that's going to be a player, but notice I use the word might, so I'm going to say option here. By the way, I'm going to dodge the whole issue of how a street mutates, so it has an owner or doesn't have an owner, how it moves between those two states. We're going to have an episode later on about mutation where we'll tackle that. Again, I missed the star off here. So that's kind of all the things we need to know about a street, but there's other types of squares on the board, so other cases in the location. A location can be a utility, which is like the electric company or the water company. It's going to have a name. It's going to have a cost. That's the cost that the player who lands on it first has to pay if they want to buy the utility. I may have not mentioned this, but the street has a price up here too. And it might have an owner, so that's a player option again. Now, I will concede there's some commonality between these cases, and if you're a kind of OO person, you'll be itching to make that into some kind of hierarchy or interface implementation. I'm going to keep it simple and just allow that little bit of code repetition there. And then similarly, another kind of thing on the board is a station, which actually has a very similar shape. So I'm going to allow that repetition there, just fix that spelling. And then I'm just going to paste in a bunch of other cases because you obviously kind of get the idea by now. So these are the other cases. So this actually will cover all the types of location on the board. There's a tax, which might be, I think, income tax or super tax. And there's others which I'm not going to provide any attributes at the moment, because for instance the go to jail location, it doesn't need a name because there's only one of it, and so forth. So that's modelled the board pretty nicely. We could just make ourselves a list of locations and we'd have a board. Now let's have some functions we're going to need in order to implement some simple play. We are obviously not in this tutorial going to model the whole of Monopoly. I'm just going to model basically what happens when a player lands on another player's location and gets charged. So, well, I said another player's location, so let's have a function called owns location. Takes a player argument and a location. And we're going to do pattern matching on the location. Now, there's only three things that even have an owner. Those are street, which takes a few things, one of which is, I think it's something like the sixth thing, which is the owner. And we're going to say, we're going to kind of have a bit of nested matching going on here. I'm going to say some owner, because when the ownership of a street is none, then obviously no one can own it. So we might as well match to that degree. And then another thing which might be owned is a utility. If you look at the pattern matching episode, I am recovering the values which must have been used to create this street, but I'm actually ignoring most of them and just recovering the owner. And then the third kind of thing that we go in is station. Actually, the payload of that is the same. So there we go. An extra bracket crept in here. So from each of those cases, I will have recovered an actual owner value. So the only thing that remained actually is to compare the owner of the street or the utility or the station with the player that we're asking the question about. So does the player equal the owner that we've recovered for that particular location? And then all the other cases, so we can just do a catch-all there, the thing can't even be owned, so the return value must be false for those. Now I've got some red squigglies going on, so let me just sort those out. Got quite a few missing brackets. Let's sort those out. I could have omitted some of these, but there we are, we've done it now. There we go, so we've got an owns location function which takes a player and a location and returns true if the player owns the location. So that's when our discriminated unions come together with pattern matching to provide a really concise way of branching our logic. Now another thing we're going to need, and you'll have to trust me until we actually use it, is we're going to need a list of all the streets of a particular colour. So we're going to take some board. We haven't even specified what the type of that is, but that's going to be pinned down in just a second when we feed it into seek.filter, which, if you haven't done filtering, is just kind of like a where clause in a SQL statement. And for a given location, because a board consists of locations, again, pattern matching, match the location with. Now only streets can have colour. So we're going to recover the colour using pattern matching again, and in that case we're going to see if the colour coming in is equal to the colour we recover. In other cases this actually is very similar in kind of structure to owns location. Nothing else can be owned, so we must return false there. So that'll take a whole board, and it's automatically defined that a board is going to be some enumerable or sequence of locations and a colour, and it'll return a sequence of locations which will just be the streets of the given colour. Now the reason we did that is because in calculating the rental for a property or a location, we need to know if the person who owns that location also owns all the other streets of that colour, because if they do, the rent is doubled. So let's say let owns streets set for a given player and a given colour on a given board. Again, take the board, pull out just the streets of the colour specified using that function we just defined. Just realised I've misspelt streets as steets there, so that sorted that out. And then within that list of just the streets of this given colour, let's see if any exist where the player doesn't own it. Because if any exists where the player doesn't own it, then that player obviously cannot own the whole set. And we just then need to reverse the logic like that. By the way, if you're wondering how I'm getting these triangles rather than the vertical bar greater than sign, I'm using a special font. I will post a link to that font in the comments of the video. Right, now having done that, we're in a position to actually charge someone if they land on a location. So I'll have a function called charge. I'm actually going to specify the types here, otherwise things get a bit complicated. So given a particular player lands on a particular location within a particular board, what should the rental that they get charged be? Well, if it's a street of a particular colour, which we'll pull out there, and a particular state of development, we're going to pull out the rental card or the rental price list, and we're going to pull out the owner of the street. Right, so now based on who owns it, well, if no one owns it, you're not going to get charged because there's no one to pay the rental to. If someone does own it, and here we're going to use a when guard, which kind of augments the logic of a particular pattern matching case when the owner of the street is not equal to the player. because if you land on your own street, again, you don't get charged. Now we need to look at the state of development of the street, which you recovered here, remember? If it's empty, so the owner of the street hasn't developed, hasn't put any houses on it at all, well, you get charged, but you get double charged if the owner of the street owns all the streets of that colour. So we need a factor of, which is going to be 1 or 2, and we're going to say if the owner of the street given the current board and the colour of the current street owns all those colours, then there's a multiplier of 2, else there's a multiplier of 1. Then we can just look at the rentals array and look at the first element. It's not very explicit in the modelling up here, but I'm assuming that the rentals are in the order undeveloped, 1, 2, 3, 4 houses, then hotel. That piece of modelling could be made a little bit more make invalid state unrepresentable, but that will do for now. So we just want to return the 0th rental, multiply it by a factor, and I'm going to say that if there's no rent due, rather than returning a 0, I'm going to be returning a none. Actually, I already said that there, didn't I? So that means for consistency we need to pipe the results of that calculation into sum, and I've also been inconsistent here in my spelling. Right, so that's what happens if the street was empty. How about if it's got some houses? Well, we're going to need to know the number of houses, so that's where we recover the payload from the development DU here. I should also say, by the way, that up here, where we optionally included a label for the payload item, that has no bearing at all on the way the payload is recovered using pattern matching. Okay, so it's almost like a piece of documentation that. Hence, I was able to say down here, just houses C. Right, so in that case, we can again just exploit the ordering we're assuming on the array of rentals and say, since there'll be 1, 2, 3, or 4 houses, we can take the cth element of the array. There's no doubling, so we can just return that directly wrapped in a sum. If it's a hotel, it's just the 5th element. Bit of a movie reference there. Right, now, so the cases we've covered as far as the owner is concerned are there's no owner, no rental. There's an owner when the owner is not equal to the player. The only other one is there's an owner and it's also the player, so that basically you've landed on your own square or your own location. We don't need to know who you are because we won't hit this line unless this check fails, so we can just directly return none here. So that's all the street cases. For the other cases, I could say something like utility. And I might want to recover the name, the rental, and the owner. But actually, I'm just simply going to, because I'm not going to do the calculations in this tutorial, I'm simply going to raise an exception. And in fact, I will do that for everything. So let's just be lazy and do that. So I could have telescoped these two things to one line, but I just wanted to show you us recovering the name, the rentals and the owner for another kind of location. So that's kind of all the modelling we need to do. So just to recap, we've got a little domain of players, a little domain of street colours, a little domain of states of development of a street, empty or some houses or a hotel. This isn't a DU, this is a type alias giving a name to an integer called price. And our kind of main domain is locations, which could be a street with some payload items, a utility like gas or electricity, a station, and so on and so forth. Then we've got some functions which, given certain arguments within those domains, recover the relevant thing, in this case whether a particular player owns a particular location or whether a particular player sorry, this is that one down there, whether a particular player owns all the locations of a particular colour, and so on. Then we pull that all together into one heroic match statement, or in fact some nested match statements, which lets you calculate how much a player should be charged. So having done all that, let's paste in some code just to demo that. So I'm just going to put a separate module in down here. So here we're creating the first few squares of a board. So our go square is just the go case. Old Kent Road is a street with a name, a price to buy the street, a colour, a state of development initially empty, a price card, and an owner, which is none. Community Chest is the next square, Whitechapel Road, another brown road, an income tax square, King's Cross, which is a station, and then just so we had a couple of colour cases, we've got the Angel Islington in there, which is a light blue street. So we can make a board just by making a list of those values, and having done that we can call our charge function. So let's imagine that Boot has landed on Old Kent Road, and given a particular board, which is that one there, how much will they be charged? So I'm going to need to send the top half of this to F Interactive. Then we'll just skip the module demo bit and send our setup in. Now, given that this is a street where no one owns anything, we'd expect when Boot lands on Old Kent Road for them not to be charged anything. So I'm going to send that one line to F Interactive. And sure enough, charged is null. Very unfortunately, nuns get rendered as null when you send them to printfn%a. But that will be a none if we were consuming this value in F# code. Let's now make a little variation on that situation. And by the way, all this logic should be in test really, but this is just a demo. So we're going to make another Old Kent Road called Old Kent Road Tick, and this time Boot is going to own it. So we'll make another board called Board Tick that uses the original values but just our amended Old Kent Road. You remember I said I was going to skip the whole issue of mutation for this tutorial. And let's do a couple of little, I won't even call them test trials here. Let's see what happens when Boot lands on Old Kent Road. They still shouldn't be charged, should they, because they own it. And what happens when Battleship falls on Old Kent Road? They should be charged that rental there because the street is empty, it's undeveloped. So let's send that lot to F# Interactive. We're expecting null here. We're expecting £2 here. There we go. So that's working pretty nicely. Let's try another situation. So Old Kent Road Tick Tick has 3 houses on but is otherwise the same. Make a board with that and do those same 2 charges. Again, Boot shouldn't get charged because they own it. Battleship should be charged the charge for 3 houses, which I think is 0, 1, 2, 3, should be 90. There we go. And we're nearly at the end. Let's make another case. Let's get Battleship to own all the brown roads. So some Battleship for the 2 brown roads we've defined. Make a board doing that. And we should find that when Boot hits this brown street, Old Kent Road, they should be charged twice the base rental. These streets aren't developed, but Battleship owns both of them. We're landing on Old Kent Road, so we should be charged 4. And there we go. So, very quick recap. Do you kind of start life in your mind as something like an enum, but you can sneak payloads into the enum. The payloads can be arbitrarily complicated, and then you can recover some or all of the payload using pattern matching. And really, if your code isn't absolutely littered with pattern matching and discriminated unions in F#, you're doing it wrong. I hope you enjoyed this casual F# video. Hope to see you again soon. Bye!